Welcome to this Nordic webinar. Today I'm going to introduce you to the Bluetooth Low Energy technology. It exists a lot of content out there trying to explain this technology already and how it works, with tutorials, guides, videos and even books. And a lot of this content comes from Nordic. But I thought still it would be valuable to do a webinar about this, especially one that included the later features like Pirection Finding and LE audio. I hope I have selected a level of detail and abstraction that you find useful. So my name is Petter Myhre and I work as a product marketing manager for Nordic. I've been with Nordic for almost 7 years. I started in a technical support team, helping customers with their wireless applications, but now I'm in product marketing, been there for 2 years, where I promote Nordic's products and technologies, both the cellular IoT and also the short-range wireless side with Bluetooth Low Energy, Bluetooth Mesh, Thread and Zigbee. So first some practicalities. This webinar will last for approximately 50 to 60 minutes. Questions are encouraged, so please type questions in the top of the right sidebar. And the questions you ask here will be anonymous, but try to keep them relevant to the topic so that the questions and answers are useful for everyone. I will answer questions towards the end. The chat at the bottom right side is not anonymous and should not be used for questions. But you can use it to discuss and chat with the other attendees. If you have more questions or your question didn't get a proper answer, please use DevZone, our developer forum, where our Nordic engineers is ready to answer. A recording of the webinar will be available together with the presentation at webinars.nordicsemi.com in a couple of days after the webinar. So this is the content for today. I will cover the basics. We'll talk a bit about why this technology is so great and how it is managed. I'll talk about the architecture, going through the different layers in the Bluetooth Low Energy stack and the specification. I'll talk about the different topologies that is possible and the different roles that we have to build topologies. I have a couple of slides on security, giving an introduction to that. Also talk about the different throughputs that you can get with the different modes and also how we can increase the range. Then I will talk about the latest features, Pirection Finding, and then in the end, LE audio. So first for the basics. So the key features for Bluetooth Low Energy. It's a wireless personal area network technology. Typically, this is designed to connect your personal devices to your smartphone or similar, but you can also extend this to other applications. It's an open standard, meaning that you have interoperability between devices and it's ubiquitous. So this means that the Bluetooth Low Energy standard is now standardized in all smartphones, tablets and laptops. In addition to a wide range of other devices. It has support in iOS and Android, as well as Mac OS, Windows 10 and Linux. It's a very efficient and ultra-low power protocol, meaning that you have very small packets and you have short RX and TX windows. So you can sleep, your device can sleep as much as possible, using the radio as little as possible. It has a very low RAM footprint. Here I have an example of 5.6 kilobyte. This is with our protocol stack. And it's very flexible, so you can have up to 1.4 megabit per second throughput and more than 1000 meter range, depending on how you configure it. So Bluetooth Low Energy is managed by the Bluetooth SIG, the special interest group. This group developed and licensed the Bluetooth Low Energy technology, and it consists of a network of member organizations. It was founded all the way back in September 1998, so it's been around for quite a long time. And it's a non-profit organization, meaning that all the fees and qualification fees that goes into this organization will be used to develop the technology even further. Currently it has 36,000 member companies, which is a quite impressive number. And actually in 2019 there were more than 4.2 billion Bluetooth products shipped. Nordic is an associate member in the Bluetooth SIG, and we are involved in several of the working groups, which help develop the different specifications. So here this slide, I added this to show the evolution of Bluetooth Low Energy. I'm not going to go into detail on all of these features, but I just want to show you that Bluetooth Low Energy has evolved quite a bit since it came around in 2010 with the Bluetooth 4.0. In 2013, this evolved to 4.1, where the main feature that was added was that you could have concurrent peripheral and central. A device could also have multiple peripheral connections. I will talk a bit more about that in a later slide, then you will understand what I mean with this. And then in 2014 came Bluetooth 4.2. It had two main features: LE secure connections, increasing the level of security that you could have between devices, improving protection against passive eavesdropping and also active attacks. It also added data length extension, which allowed larger payloads in each packet, reducing the overhead, increasing the maximum throughput that you can get through your link. Then you have Bluetooth 5, which all of you probably have heard about. It added 4 new features. You had the 2 megabit per second feature, so up until then you can only have 1 megabit per second bitrate, allowing to have much higher throughput and also more efficient transfers. It also added the long range feature, increasing the range of your connection with up to 4 times. Both of these features I will cover in the later slides in detail. It also added advertising extensions, allowing you to put much more data into the non-connect or the advertising packets, what you use to broadcast information. It also opened the possibility to have a 20 dB max TX power compared to 10 that was before. Then in 2017 the Bluetooth mesh profile was added. And this is a networking technology supporting concurrent multicast and allows you to build up large-scale networks. Then last year came Bluetooth 5.1, adding the Pirection Finding feature, allowing devices to figure out where they are relative to another device. I have some slides on that as well. And then earlier this year came Bluetooth 5.2, which is the first step towards enabling LE audio with the isochronous channels, allowing you to stream data to one or more devices. It also added LE power control, which enables TX power to be dynamically changed by the peer, depending on the received signal strength. Enhanced attribute protocol was also added here, and this introduced concurrent transactions. And this can reduce latency when multiple applications are using one Bluetooth Low Energy stack. And Bluetooth SIG has also announced that LE audio is coming soon. So then over to the architecture. So we kind of have three main blocks. You have profile, you have the host, and you have the controller. The host and controller is what is looked at as a typical Bluetooth Low Energy stack, and then you have the profiles on top, which define some kind of specific application typically. Between the controller and the host, you have the host controller interface. This makes a natural split if you want to have controller on one device and a host on another device. It is also beneficial if you have a device with multiple cores, like the nRF5340, where you can have the controller in the network core and a host in the application core. Let's have a closer look on this. So profiles. They describe how two or more devices can discover and communicate with each other. They typically implement a specific application, for example, heart rate. So it defines how one device kind of uses a sensor to get the heart rate, and then how another device can discover this device and extract the heart rate from it. It can be standard or proprietary. So you can see most of these are standard, the alert notification all the way down to proximity. But you can also have proprietary profiles that you can use. And each profile has its own specification. And these are open, so you can go and have a look at them if you are interested. Then we have the host, and this contains the host contains the upper layer of the Bluetooth Low Energy protocol stack. At the bottom you have the logical link control and adaptation protocol, also referred to as L2 cap. This is a multiplexing layer for different higher layers of the protocol. You have the attribute protocol, AT, and this implements a simple client-server model, where one device has the server and the other device is a client and access the data on this server. The data in this context is called attributes. Then you have the security manager protocol, and this defines a protocol for pairing and key distribution, which you use to authenticate and encrypt the link. Then you also have a GATT inside the host, and this is a generic attribute profile. This is the highest data layer, and it uses AT to discover and access attributes. And it also specifies a hierarchical structure of attributes, defining how these can be structured into services, characteristics, and descriptors. Services are top-level containers and typically correspond to some kind of primary feature of a device. And inside the service you have one or more characteristics, which are individual items of state data. And then you can have descriptors belonging to a characteristic, giving some more information about the characteristic. Then you have the GAP, generic access profile, and this is the highest control layer. This defines the device roles, which I will explain soon. And it also defines how devices can discover and connect to each other, and defines the different security modes and procedures. Then over to the controller. It has two layers. It has the link layer and the physical layer. The physical layer defines how two radios can send bits to each other using radio waves, while the link layer defines the link layer states, defines the different address types and device addresses, and also the packet format that is used. A few more details about the physical layer or the radio. So it uses the 2.4 GHz ISM band, which is a global band, so you can use Bluetooth Low Energy devices all over the world. It uses 40 RF channels, 2 MHz in each. It uses GFSK modulation or Gaussian frequency shift keying. And here you can have the option between 1 or 2 mega symbols per second. One symbol is typically 1 bit, except if you're using the long range mode, which I will explain later. And you can have up to 20 dBm TX power. Then over to topology and roles. So the gap roles are listed on the left side here, and they are tied to different link layer states. So you have a broadcaster. This can only advertise, which means that it can broadcast packets, which is non-connectable. Then you have an observer, which can scan these packets from the broadcaster. And then you have a peripheral role. This can advertise and also enter a connection as a slave. Then you have central, which can scan. It can also initiate connections. And when it goes into connection, it's a master. So let's have a closer look on that. So here you see a broadcaster to the left that is advertising, and you have an observer which is scanning. Here you have a central, and this can also scan for the advertisements from the broadcaster, but it cannot connect to it because a broadcaster does not support connections. But if you have a peripheral over here that is advertising, a central can send a connection request to it and establish a connection. And a central can have multiple connections to peripherals, and in the first spec this was the only possibility. You can only build a Piconet or a star network topology. But then in 4.1 the concurrent central and peripheral was added, meaning that you could have a device or a radio that supported both central and peripheral. You could also have a peripheral that supported several connections. So here you see that the peripheral here is already connected to the central, but it can still advertise, and then the central can send a connection request to it and establish a connection. Then the peripheral in this device can start to advertise, and then this central, for example, can connect to it. So from 4.1, from specification 4.1, you could not only build Piconets or star networks, but you could also build more advanced scatternet topologies. And I just want to mention that our protocol stack supports up to 20 concurrent links in all combinations of central and peripheral, while at the same time being a broadcaster and observer. So it's very flexible what you can do here. Then I just wanted to add a more specific example where you use these roles together. So here you have a heart rate belt and it's a peripheral, and it's connected to the central in the smart watch or GPS watch. And then the peripheral role here is connected to the central, which is a smartphone. Then over to security. So first, some terminology. You have pairing and bonding in Bluetooth Low Energy. So pairing is authenticating another device by establishing temporary shared secret keys, which can be used to encrypt a link. Bonding is pairing followed by a distribution of keys, which can be used to encrypt the link in future reconnections. So So you have a couple of procedures that is good to know about. You have authentication and encryption. So each time two devices connect, the connection operates with no security. Then a high level of security can be achieved by performing either an authentication procedure. Here the type of pairing determines the security level. So you have some different methods and those result in different security levels. Then if you are also bonded, you can use the encryption procedure to encrypt the link. So then you already have the encryption keys and you encrypt the link by using this procedure. And here it's the original pairing that determines the achieved security level. So you have two types of pairing. High-level pairing in Bluetooth Low Energy, you have the legacy pairing. And this is the one that was introduced in Bluetooth 4.0. It has three methods. Just works, which is no authentication. And it does not protect against any attacks. You have passkey entry, where a six-digit value is shared between the devices using their I/O capabilities. So typically a screen and a keypad. And you have auto-band, where encryption keys based on data transferred by other means is used to encrypt the link. And the typical one here is using NFC. Legacy pairing is not recommended by the Bluetooth SIG to use, but if you must use it, you should use auto-band. Then we have LS secure connections. This was added in specification 4.2 back in 2014, and it provided much better protection against eavesdropping and also better protection against man-in-the-middle attacks or active attacks. It uses FIPS approved algorithms, and it also uses this elliptic curve Diffie-Hellman key agreement. This allows two peers, each having a public-private key pair, to establish a shared secret key over an insecure channel. This secret key is then used to derive encryption keys that is used to encrypt the link. And all of these, both legacy pairing and LS secure connection, uses 128-bit AES encryption. This is what is recommended to use by the Bluetooth SIG, but you should avoid using JustWorks as it's an authenticated pairing. Unauthenticated pairing. So you have some different pairing methods in LS secure connections as well. You have JustWorks, where you just connect and there's not really any authentication. You have passkey entry, where a 6-digit value is shared between the devices using their I/O capabilities. This passkey entry is different from the legacy pairing. It's much stronger. It also added this numeric comparison, where a 6-digit value displayed on both devices is confirmed by both sides by the user pressing OK. Then both devices need to have a display and some kind of interface to say that the numbers are equal. It also supports auto-band, OOB, and here the encryption keys are based on data transferred by other means, for example NFC, which is the recommended way to do it. Then I want to say a few words about throughput and range when it comes to Bluetooth Low Energy. So in the first specifications, in 4.0 and 4.1, you had the 1 megabit per second data rate, and you could have a 27-byte payload in each packet. With this, you could achieve up to 305 kilobit per second if you use the entire radio time. In Bluetooth 4.2, the data length extension feature was added, where you could have longer payloads in your data packets, up to 251 bytes. And this increased the throughput up to 803 kilobit per second. And then in Bluetooth 5, the 2 megabit per second data rate was added, increasing the throughput up to 1434 kilobit per second. And the blue squares here, you can see that the height of these are proportional to the throughput, while the range, maximum range, is proportional to the width. So you can see that the box on the right is a bit smaller, and this is because this high throughput 2 megabit per second has a bit shorter range, approximately 29% range reduction. But this 2 megabit per second feature wasn't only about increasing the throughput. It also transfers the same amount of data in half the time that the 1 megabit per second mode does. This may not sound too impressive, but the current consumption of the radio is similar when receiving and transmitting in both modes. The result is that you are using close to half the energy sending the same amount of data with 2 megabit per second compared to 1 megabit per second, making it much more energy effective. So here you can see on the top I have the 1 megabit per second mode, and I've taken these current numbers from one of our devices, the nRF52810, and you can see that in RX and TX it uses 4.6 milliamps. At the bottom we have the 2 megabit per second, and you can see that it's spending approximately half the time in both RX and TX, and the RX current is a bit higher while the TX current is the same. So the result is that it's close to half the energy consumption. Also, with the 2 megabit per feature, each device is spending less time on air. This improves coexistence and reduces congestion, which is more and more important when the number of wireless devices is growing. It also enables a single device to maintain more connections, cutting the necessary radio time slots needed by each connection in half. And this is especially beneficial for central devices like smartphone or tablets that may have many peripherals connected at the same time. So I often get this question, what is the range? And what I can say, it's not a few meters. We have done tests achieving more than 1300 meters, and this was without the maximum allowed TX power. It was with 0 dBm TX power. But it's very difficult to give one specific number on this, because it highly depends on the environment. If it's indoors, outdoors, how much interference it is, and stuff like that. But with our SoCs, we support up to 8 dBm TX power, and this is more than enough for most applications. And increasing the TX power reduces efficiency and increases peak currents, of course. 20 dBm max TX power was introduced in Bluetooth 5, and with our devices that is possible by adding a range extender. For example, our nRF21540 RF front-end module. But it is important to know that there are limitations on the regulatory restrictions in the different parts of the world. So in Europe, it's ETSI that we follow, and this has a limitation of 10 dBm when you advertise and 13 dBm in connection. While FCC in the US allows 20 dBm. Also, the RX sensitivity of the radios have improved significantly the last years. Our latest SoC, the nRF5340, has minus 97.5 dBm sensitivity. And it's also possible to improve this further by adding a range extender, for example our nRF21540 RF front-end module. You can also extend the range by using Bluetooth long range, which was introduced in Bluetooth 5. And this uses standard 1 megasymbol per second modulation, which typically means that one symbol is 1 bit. But with Bluetooth long range, it uses up to 8 symbols per bit, resulting in 125 kilobit per second effective data rate. But it gives 12 dB increased sensitivity, which theoretically results in 4 times the range. But it reduces efficiency because it has to use up to 8 symbols transmitting and receiving per bit. The benefit is that you don't really need to add anything to your PCB to use this mode. You can just have it there and use it if you need it in a product. And it does not increase peak currents. Then I have a slide here that visualizes the range that you can achieve compared to the 1 megabit per second mode. And you can see that the throughput, max throughput here with the long range mode is 113 kilobit per second. And here you also have the 2 megabit per second mode. So I would say that these modes adds a lot of flexibility to Bluetooth Low Energy. You can choose to have high throughput and a bit shorter range, or you can have long range with lower throughput. And the requirements of a product may change over time. Maybe you want to use high speed for device firmware update, while you want to use long range for normal operation, or when you cannot get a connection with using 1 megabit per second. Because these modes can be changed dynamically, so you can use RSSI, for example, to change from 2 megabit to 1 megabit or to long range if that is needed. Direction finding. So this was part of Bluetooth 5.1. It was a hallmark feature there. And this was adopted last year, January 29th. And it requires radio changes. So older Bluetooth low energy radios cannot use this feature. It's an optional feature, so it's not something that you have to use. And what it does is that it enables positioning solutions to not only rely on received signal strength indicator, but can also use the actual direction of a signal. So here I have some direction finding use cases. So you have asset tracking, where you typically build a real-time locating system. And this is part of the positioning system use cases. You also have wayfinding, which is also called, it's typically used in indoor positioning. And then on the right side you have proximity solutions, where you have point of interest or proximity marketing, which can be used in, for example, museums, so that you can have beacons or tags in different items in the museum, and when you approach it with your smartphone, you get some information about the item you're looking at. You also have item finding, which enables where you can use direction finding to build more advanced item finding solutions. So you can have a tag that you can locate with with a smartphone, for example, where you not only use the received signal strength, but you can also get a direction where you should go to find your things. So you have two options when it comes to direction finding. You have angle of arrival, AOA, and in this setup, the transmitter is just a simple beacon or a tag. It has a single antenna and no IQ calculations are needed in this device, so it can be a simple device. And then on the receiver side, this has to be fairly advanced. It has an antenna array with multiple antennas and also an RF switch so that it can listen on these different antennas. And here this device has to calculate the angles by using the IQ data. And this device can calculate the angle of the arrived signal. Then you have angle of departure, where the roles are kind of turned around. Here the transmitter is simpler, but it has an antenna array and one or more RF switches. But no IQ calculations are needed in this device. So here this will send a signal on each of these antennas at different times. And then the receiver can scan these signals at different times and calculate the IQ data of the departure signal, or the angle of the departure signal. So the receiver only needs a single antenna, but it has to calculate the angles. So what use cases use AOA and which use AOD? So for asset tracking or real-time location systems, you typically use AOA, and then you typically have multiple receivers at fixed locations. And then the transmitter or tag can be a beacon on a box in the warehouse, for example, or it can be a smartphone that track a person. You have wayfinding, where AOD typically is used, so that you have multiple transmitters at fixed locations, typically in the roof. And then the receiver is typically a smartphone, and it's able to figure out where it is relative to the transmitters. Another use case for this is that you have an autonomous robot, for example, that should figure out where it is in a warehouse. Then you can use AOD as well. Then you have point of interest. Here you use AOD, and the transmitters are typically on the things that you want to navigate to, and the receiver is typically a smartphone here, where you get up your information about the thing that you're approaching. Then you have item finding, where you only need a relative direction compared to the thing you're trying to find. And the receiver is typically a smartphone, and a tag is typically a beacon on the thing you're trying to find. Then I wanted to extend a bit on this asset tracking or real-time locating system. It uses the angle of arrival method. And a tag is a simple transmitter. And then you have several locators at fixed locations around the area, typically in the roof. And then each locator determines the direction of the signal, calculates the angle, and then this information is sent to the location engine from both or one or more locators. And then it's the location engine that determines the position of the tag. Okay, LE audio. So with LE audio, Bluetooth audio is split into two. You have the classic audio, which all Bluetooth devices uses right now, and you have LE audio, which is audio over Bluetooth Low Energy. And this was announced earlier this year, January 6th. And it added four main new features, or talked about four new features. Isochronous channels, and which allows streaming data to one or more devices. A new audio codec, LC3, which is a high quality, low power codec. It added a feature called for earbuds, allows you to stream audio to two earbuds at the same time. So it's an independent stream to each earbud. And broadcast audio for audio sharing. And this enables audio to be streamed from one device to many other devices. So isochronous channels. This is part of the Bluetooth Low Energy stack. So it allows audio streaming to one or more connected devices. And these channels are synchronized so that you can get from a smartphone you have one channel to each earbud. And these channels are synchronized so that you can get synchronous sound. This is not possible with Bluetooth Classic. Then you would have to transfer the audio to one of the earbuds, and then that would relay one of the channels to the other one. And this is not ideal, either from a quality perspective or from a power perspective. It also enables audio broadcasting to multiple devices. So you have a new audio codec, LC3, stands for Complexity Communications Codec. It's a high quality, low power codec, and it's mandatory to use for LE audio. And if we compare it to SBC, which is the mandatory Bluetooth Classic audio codec, you can see that it has 50% improvement in perceived audio quality when using the 240 kilobit per second bitrate. And it's also interesting to see that if you use 160 kilobit per second bitrate, the perceived audio quality is still pretty high compared to SBC. So it's much more efficient and low power. It's also a very flexible codec, so that you can do a trade-off between audio quality and longer battery life, or smaller products, or smaller batteries. Smaller batteries leads to smaller products. Then you have multi-stream audio for earbuds, so you can have better performing earbuds. You can have one channel to each earbud, which are synchronized and independent. And it also enables for smoother transitions between audio source devices. So if you want to move from you're listening to your smartphone and then you want to listen to your PC, this should be much smoother with LE audio. Then you have broadcast audio for audio sharing. And this enables unlimited number of sync devices from one source. And it enables some new use cases. The first one is they call personal audio sharing, which consists of shared listening and shared watching. Shared listening means that you can several people can listen to one source with their audio headsets, for example, headphones. And shared watching, you can watch a movie on your iPad or on a TV, and you can get the sound to several headphones at the same time. And then you have location audio sharing. And this is very beneficial, for example, for public TVs. It means that you can connect your headphones to a public TV and listen to the audio without disturbing everyone else that's in the airport, for example, or in a bar where you're watching your favorite football game, or in the gym, and so on. It also enables translation possibilities, where you can have different audio streams from a public TV in different languages or in conferences. And it also provides hearing assistance in many of the same places, cinemas, theaters, but maybe also, most importantly, in lecture halls. That's what I had. I just want to mention again the Nordic Dev Zone. If you have questions or you get into trouble, please go here and ask your question, and other developers and Nordic application engineers will help out. Then it's time for questions. Let me see what we have here. So I hope you guys can hear me. The first question is about when Nordic will have a direction finding solution, and that is something that we are working on, and we are aiming for second half of 2020 for that. It will be hardware, software, and documentation. We will aim for angle of arrival first. And this is mainly because of most of the AOD use cases require support in the smartphone. Or with AOA, you can build a real-time locating system with Nordic devices in both the locator and the tag. So we will have a reference design or a demo design with a transmitter tag and also a receiver locator. And it will include multiple antennas and RF switches. And it also provides some software on how to calculate the IQ samples. Then we have a question, will NR53 or NR52 be able to support simultaneously LE audio and native BLE for data transfer? I'm not 100% sure on this, but I'm pretty sure that we will be able to do concurrent LE audio and BLE data transfer. But you only have one radio with a finite radio time, so this needs to be managed somehow, so that you have enough throughput for your audio transfer. How do I calculate approximate distance with RSSI? Is there any statistical algorithm available for the same? This is in general very difficult to do with RSSI. What we typically recommend is that you can have kind of room accuracy, that you can figure out if something is in the room. But if you want better accuracy than that, direction finding is the way to go. Then And there's a question, more than 1,000 meter range. Yes, that should be possible, and by using long range or using a PA LNA. But as I mentioned, we have achieved 1,300 meters outdoors with long range mode and 0 dBm output power. What is the package size for 1 megabit per second and 2 megabit per second? That's up to 251 byte payload in both modes. Why is Nordic's BLE offering superior to other competitors? What can you do better than others? In general, our ICs are of very good quality, and we are known for that. We have very high market share, up to 50%, and our protocol stacks are very mature, and they are interoperable with almost any smartphones, and we are very proud of that. So that's why many of our customers are choosing us, because of our protocol stacks and our low power, high quality ICs. How many concurrent connections can be made in a peripheral and central? So as I mentioned, with our stacks, you can have 20 connections as a peripheral or as a central, or a combination of these. What is the least amount of latency that can be achieved between a central and several peripherals? So the minimum connection interval is 7.5 milliseconds. So that kind of determines the latency. And then you have to, if you have several connections, you have to time slot these. So it depends also how much data you're sending. But if you're sending just a very small amount of data, you can achieve this latency with several devices, as long as you're not losing packets, of course. What security features are available to avoid replay of beacons? You have replay protection attack, but that's only if you are in a connection and you have encrypted the link. Then you have some counters there so that you can avoid having replay attacks on your device. Once a central and peripheral, or two devices in general, are paired using JustWorks, then once they are paired, is the post-pair connection secure? Yes, this is a good point. I guess I was a bit unclear on that. If you pair with JustWorks in a safe environment, and you know that the device you are pairing with or bonding with is the one that you want to bond with, then later connections will be secure as well, because then you already have these encryption keys and you know which device you are connecting to. Is there a way to hide the NRF BLE advertising name so that it is not visible to casual BLE users from connecting, but not and only my central devices? So you can identify your device with something else than a name in the advertising packet, for example, by using a unique 128-bit UID. There are also some features that if you have bonded, you can have a random address, and you can have only your central device to recognize your peripheral. Are the data rate mentioned maximum rates for 20 simultaneous connections or just one connections? Can all 20 connections run at 1400 kilobit per second? All of these numbers are for one connection, and if you have more connections, you have to split this throughput between the devices. Because when you run at full throughput, you are using the full radio time. TX current is lower than RX current. Is it a type on the slide? No, this is correct with 0 dBm. But if you increase the TX power, that will be higher than the RX current. Can you also tell about the coexistence features with respect to other technologies like Wi-Fi and Zigbee in the same 2.4 gigahertz band? Frequency hopping is one important feature for coexistence, but what other measures are taken by using Bluetooth? Firstly, it's when you're advertised, you have 3 different channels that you advertise on, and these channels are kind of in between the typical frequencies used by Wi-Fi. And then when you go into connection, you have frequency hopping, and that's kind of the feature that tries to handle this coexistence. And there you jump between all the other 37 channels to avoid interference. And you can also block channels if you see that they are not usable, for example, and only jump between the channels that are left in the channel map. How much does a typical BLE SoC cost? That varies quite a bit. We have SoCs down to less than $1, but we also have more powerful devices with more features, more security, and so on that cost a bit more. And it really depends on what type of application that you are building and what kind of features that you need. Will the range extender still improve sensitivity in long range mode? If yes, by around how many dBs? Here the answer is yes, that will still improve the sensitivity. How many dBs? I'm not 100% sure. I would say 3 or 4, around that area. Does the data rate range change initiated by the peripheral and central both? As most of the other things in Bluetooth Low Energy, it's the central that kind of dictates everything, but the peripheral can request to change the data rate or go to long range mode. You can also have an asymmetric connection here, meaning that you can have long range in RX and normal in TX, for example. Is the direction finding supported in the nRF52832 and the 52840? Here the answer is no. You need to have some hardware changes to implement the direction finding, both for the tag and for the receiver. So then it's the 52811, 52820, and 52833, and also the nRF52840 that is capable of doing direction finding. So direction finding is required to fix the tag in a fixed location. Yes, that is what we recommend to use if you want to have a more accurate location. What are the implications of having to do IQ calculations for the device? So calculating the IQ data is standardized, but you also you need some kind of algorithms for calculating the angles from the IQ calculations, and this have to run in the device as well. And this is part of what we will provide with our solution coming out in the second half 2020. How many receivers are required to track the beacons? Well, you need at least 2. And the more you have, the more accurate position you get. It also depends on how these locators are built, how many antennas they have, and how good they operate. And is the height of the mounted receiver affect the tracking accuracy? Yes, the distance will affect the accuracy. Which features of Bluetooth 5.2 are not supported in nRF52 and nRF53 series? All devices in nRF52 series and nRF5340 are Bluetooth 5.2 SoCs, and they are capable of all the features introduced in Bluetooth 5.2. And we are working on adding software support for these features as well. Can we combine direction finding and long range? I think that is possible. Can the isochronous streaming be used for data instead of audio transfer? Yes, you can stream any data using isochronous channels. Does LC3 embed in the NRF series? Yes, that is a codec that would run inside the device typically. Let's see if we have any more. Oh, there's a lots of questions. Let's see here. I've answered many of these. I just need to sort through them. Sorry. What is the difference between passkey and LE secure connection and passkey and legacy pairing? I don't remember the details on that, but the passkey in LE in legacy pairing could be brute forced because it's only the 6-digit key, but in LE secure connections you have some additional things, or you use the Diffie-Hellman key exchange to do this in addition. So the 6-digit is mostly used for the authentication, not for the encryption. Is nRF52811 capable to perform AOA and standard data transfer simultaneously? And the answer there is yes, but in general we recommend to use the nRF52811 as a tag in an AOA setup because it has a limited amount of memory, but then it's kind of only in this setup, it's only sending out a beacon packet, so you can have a standard data transfer simultaneously with this device. In a central peripheral device, what defines the limit of these 20 connections? The limit of 20 connections, you can have more than, in principle, you can have more than 20 connections, but that is just a limit that we have set on our soft devices because we think that will cover most use cases, and you have a limited amount of radio time, of course, and if you have 20 connections, you have to split this across all the connections. So, and the more connections you have, the more RAM you will use. So it's actually the RAM and the radio time that kind of limits how many connections that is feasible to have in one device. Can we stream one device on left earbud and another device on right earbud? Yeah, that shouldn't be a problem. But then you would have problem if you have two different devices. You would have problem synchronizing, of course. Is the NRF21540 evaluation kit already available for purchase? It is not right now, but if you're interested in that, I suggest that you reach out to our sales department, and we will also launch this in not too long a time, hopefully in Q2, maybe early Q3. There's a known limitation of discovering BLE devices in a congested area. For example, conferences. What are some good practices solution Nordic offer for this problem? A good solution here is that if you build an app and you want to connect to your device, you should build an identifier into the app so that it knows which device it is looking for, so that you don't need to scan for all the other devices. Then you don't get this long list in the smartphone that you have to pick the right device. You can use a UID, for example, or an advertising name. Would you ever use a BLE solution for asset tracking, or would a cellular IoT solution be more appropriate? Well, it depends really on if you're making a solution that is supposed to work outside and inside. If you're only inside, BLE as a direction finding is a good solution. With cellular IoT, you can do tracking outside, both using GPS, which our device have, or you can also get a rough position by using the distance from the base stations, and you can also get a rough position with cellular IoT indoors, but the GPS doesn't work that well. So it's also a possibility to kind of combine these solutions, that you use BLE direction finding indoors, and then you use the cellular device when you're outdoors. Are there plans of supporting nRF52840 in new SDK? Yes, I guess you mean the NRF Connect SDK, and we have already development support for the nRF52840 in that in NRF Connect SDK, the master branch, so you can evaluate that solution now if you want to do that, and then production support is also coming very soon. Can you have LE coded PHY and LE non-coded PHY in the same device? Yes, that is possible, and you can also switch between these modes depending on what your application needs. And as I mentioned, having LE coded PHY doesn't really add any extra components or anything, so you can just have it in device just in case. Okay, that's 10 minutes over time, so then I think I will close the webinar. Thank you everyone for listening, and I will put a recording and the presentations on webinars Nordic Semi webinars.nordicsemi.com hopefully tomorrow.